Hello, welcome to chemistry class. Today's class, I'm going to explain you about semiconductors. What is a semiconductor and where are they in the periodic table? Once if you see in the periodic table, here the yellow color ones, the red color ones are the metals and the blue color ones are the non-metals and the yellow ones are the metalloids. The yellow ones are the metalloids. These metalloids are called as the semiconductors. So, what are the properties of the metals, non-metals, and metalloids? We'll see. So, there were different theories explained for us based the theories of bonding in the metals. The theories are we are having free electron theory, valence bond theory, and band theory. Any theory of the bonding in metals, it should account for the characteristic properties of luster, complete opacity, high thermal electrical conductivities, applicability of Ohm's law, applicability of the Franz law, the ratio of the thermal conductivity to electrical conductivity. How is it constant or not? What is the variation of resistivity in presence of external magnetic field? In order to account these properties, theories are proposed. A valence bond theory, yeah, that was good. It gave the synchronous resonance on non-ionic forms for the lithium. For the different metals. The ionic resonance forms, what are the resonance structures were given. But there is not clear cut explanation of the different materials. And coming to the free electron theory also, that was some, yeah, good, but there are still some drawbacks for the free electron theory. Coming to the third theory of the bonding in metals is the band theory of solids. Band theory was successful in explaining electronic thermal properties of metals, and namely some specific heat, paramagnetism. All such properties were explained. Nevertheless, other properties couldn't be explained by the free electron theory. Even there are some drawbacks for the valence bond theory, complete explanation was not given. So consequences for the basing on the band model molecular orbital theory, we got the compounds with we are able to understand what is a metal, what is non-metal insulators, and what are the semiconductors. And now today we are going to discuss about the semiconductors in detail. What are the different types of semiconductors? Today's topic is only about the semiconductors, concept of the semiconductors we'll see. Semiconductors are materials whose electrical conductivity lies between the conductors and the insulators. These are the electrical conductivity lies between those of conductors and the insulators of semiconductors. Now, can be semiconductors can be crystalline, amorphous solids. It can be a crystalline and that of the amorphous solids. Now, there are high resistance, higher than the typical resistance materials, but still much lower resistance than the insulators. So, what are the types of insulators? Diagram, carrier concentration, application of semiconductors, organic semiconductors, superconductors. Types of semiconductors, Meissner effect, Coopers. There are different contexts for them. Semiconductors are the materials whose electronic properties are intermediate between metals and the non-metals. So semiconductors are the materials whose electronic properties are intermediate between the metals and insulators. They have the conductivity range of 10 to the power of minus 4 and 10 to the power of 10 to the power of minus 4 to 10 to the power of plus 4. The interesting feature about the semiconductors is that they are bipolar and the current is transported by two charge carriers of oppositely charged. The intermediate properties can be determined by crystal structure, bonding characteristics, and electronic energy bands. I've told you here in the periodic table where they lie. Here, these are the metals, this is semiconductors, and these are the non-metals. So silicon example will take silicon, germanium are the elemental semiconductors. They have four valence electrons which are distributed among the outermost s and p orbitals. These outermost s and p orbitals of semiconductors involve sp3 hybridization. The sp3 hybrid orbitals form four covalent bonds of equal angular separation leading to a tetrahedral arrangement of atoms in the space, and it results in the tetrahedron shape, resulting the crystal structure is known as the diamond cubic crystal structure. Now semiconductors, we can say types. Pure semiconductors are intrinsic and impure semiconductors are extrinsic. See, before that, we should know the properties. Before explaining the complete um, information about the semiconductors, I should give you some explanation about the metals and insulators. In the metals, you can see this is the valence bond and this is the conduction band. Both the bands are almost overlapping, and therefore the electrons can jump from valence bond to conduction band. And coming to the insulators, the valence bond and conduction band, there is a large gap and a Fermi level is there. This bond gap inhibits the jumping of the electrons from valence bond to the conduction bond. And now the semiconductors, you can see a Fermi level. This the red one is the conduction band, and this blue one, the red one is a valence bond, and the blue one is the conduction. Here the energy gap between these two is very less. Energy gap between these two is very less. Therefore, the electrons can jump. In normal conditions, they don't conduct the electricity. But when the temperature is increased, you can see intrinsic semiconductor. And sometimes the impurities addition can induce the conduction for the semiconductors. So normally these are the non-conductors, and in the special conditions they are the conductors. So what we've discussed is the properties they lie in the semiconductor. It is having the property in between to that of conductor and the insulator. Semiconductor which does not have any kind of impurity, it behaves as the insulator at 0 K. And it behaves as the conductor at high temperature. Insulator at 0 K and conductor at high temperature. This is intrinsic semiconductor. These are pure semiconductors. Now, germanium and silicon, the fourth group elements, these are the best example for the extrinsic semiconductors that possess diamond-like cubic crystal structure. Yeah, we can see later on the intrinsic semiconductors, valence shell, covalent shell, how they're changing. There is a Fermi energy level, and the energy gap between these two is almost 3 electron volts, which is very less for jumping of the electron from conduction band to non-conduction band. The gap is lesser here. So It is less than the delta E is almost less than 3 electron volts. So it jumps from the energy gap is enough for jumping of the electron from valence band to the conduction band. Now we'll see the carrier concentration for this, how it is there. Before that, let me classify semiconductors. Types of semiconductors, as we have discussed, you are having extrinsic semiconductor, intrinsic semiconductor. Extrinsic semiconductors carrier concentration here in the intrinsic semiconductor, when a suitable form of energy is supplied to a semiconductor, electron takes transition from valence bond to conduction. Hence, a free electron in the conduction band and simultaneously free hole in the valence bond is formed. So this phenomenon is electron hole pair generation. So when a suitable form of energy is supplied to semiconductor, then electrons take transition from valence bond to conduction band. Hence, a free electron in conduction band and the simultaneous free hole in the valence bond can be observed. This is electron hole pair generation. In intrinsic semiconductor, number of conduction electrons will be equal to number of vacant sites or holes in the valence band. Okay, so in the intrinsic semiconductor, number of conduction electrons will be equal to the number of vacant sites or the holes in the valence band. So this is the case, this is the carrier concentration of the intrinsic semiconductor. Intrinsic semiconductor, number of conduction electrons are equal to the number of vacant sites or holes in the valence band. We'll see the extrinsic semiconductor. Extrinsic semiconductor. Extrinsic semiconductors are those extrinsic semiconductors are those in which impurities of large quantity are present. Impurities of the large quantity are present. Usually impurities can be either be third group or it can be from fifth group elements. So based on the impurity present in the extrinsic semiconductor, they're classified into n-type and p-type. So impurities are present, then that is extrinsic. Yeah, you do the doping. By doping mechanism, you can see. So the intrinsic semiconductors doped with pentavalent impurities, they can be doped with the trivalent impurities. So the energy, electron energy, you can see the valence bond and this one donor distance, it's lesser. What is the carrier concentration? What is the Fermi level variation with temperature? We'll see. What is the Hall effect? Yeah. What is a P semiconductor? We'll see. Where are the applications? How it is? So we will see. What is the carrier concentration? How? What is the Fermi level? Here I've told you the Fermi level. Yeah, this is the Fermi level. To start with, the increase of temperature EF increases slightly. As the temperature is increased, more donor atoms get ionized. Further, increase in temperature results in generation of electrons. The hole pairs due to the breeding of the covalent bonds and the materials tends to behave in intrinsic manner. So the Fermi level gradually moves towards the intrinsic Fermi level E2. Okay. To start with, the increase of the temperature EF increases slightly. EF energy also of the Fermi level will increase. So as you increase the temperature, the energy of the Fermi level increases. As temperature increases more and more, donor atoms gets ionized. Further increase in temperature results in generation of electron hole pairs. And due to breeding of the covalent bonds and the materials tend to behave as intrinsic manner. Intrinsic conductors can be observed. So the energy level gradually moves towards the intrinsic formula E2. Even at a relatively low temperatures, acceptor atoms get ionized. Yeah. Even at relatively low temperatures, these acceptor atoms get ionized. They take electrons from the valence bond and thus they give rise to the holes in the valence bond for conduction. And due to ionization of the acceptor atoms, only holes and not electrons are created. Not the electrons are created. So here, even at low temperatures, these acceptor atoms are getting ionized. They take electrons from the valence bond and they give rise to holes in the valence bond for conduction. So due to ionization of the acceptor atoms, only the holes and not the electrons are created. Thus, the holes are more in number than the electrons, and hence, holes are majority carriers and electrons are minority carriers in p type semiconductors. In the p type semiconductors. And what is the Hall effect we have to see? For the semiconductors, what is a Hall effect? Thereon, we'll see the types of semiconductors. When a magnetic field is applied perpendicular to a current carrying conductor or semiconductor, voltage is developed across the specimen in direction perpendicular to both current and the magnetic field. This phenomenon is called Hall effect, and the voltage so developed is Hall voltage. I'm repeating, when a magnetic field is applied perpendicular to the current that is being carried by the conductor or a semiconductor. Magnetic field is applied perpendicular to the current which is being carried by the conductor or the semiconductor. So voltage is developed across the specimen in direction perpendicular to both current and the magnetic field. So a voltage will be developed perpendicular to both the current and the magnetic. That is called Hall effect. There is a voltage development perpendicular to the current and the magnetic. So that is called as the Hall effect. Now there you can see the applications. So first we'll see the types of the semiconductors. Types of the semiconductors. The extrinsic semiconductors are intrinsic semiconductor and extrinsic semiconductors. You are having intrinsic semiconductors, extrinsic semiconductors. Pure form of semiconductor is intrinsic semiconductor. Pure form of the semiconductor is intrinsic semiconductor. Germanium, silicon is the example. Next, here. Number of electrons is equal to number of holes. Now, we'll see the second type is the impure type of semiconductor is extrinsic semiconductor. You are having N-type and P-type semiconductors. N-type and the P-type semiconductors. N-type negatively charged. It is due to negative ions. N-type semiconductor. And P-type, it is due to the positive holes. Now, pentavalent impurities are doped. Example like phosphorus, arsenic, antimony, etc. The donor impurity. The donor impurity. Na is more than NH. Electrons are more than holes. Number of electrons are more than number of holes. For the semiconductor, you're having 4 holes. If there are 5 electrons occupying the 4 holes, then that is N-type. So one minus is more than the base. Therefore, you get the conductor that is n-type semiconductor. Next, coming to the p-type, trivalent impurity. P-type, it is due to the positive charge. Next, here gallium, boron, indium, aluminum. That is the p-type semiconductor. Here the donor impurity, holes are more than the electrons. So more are the holes and less are the electrons. So holes are more means the pluses are more, and due to the plus, you get the conductivity. So you got this. Due to the positive charge, you get the conductivity that is called the p-type semiconductor. Now, what are the intrinsic semiconductors? An intrinsic semiconductor is one which is extremely pure form. Examples are pure germanium, silicon. These have forbidden energy gaps of 0.72 electron volts, 0.72 electron volts, and 1.1 electron volt respectively. The energy gap is so small and it is defined as one in which the number of conduction electrons is equal to number of holes. This is intrinsic semiconductor. So this is the pure form of the semiconductor where the conduction is due to the temperature. It is not due to the doping or external impurity. So pure germanium and silicon, they have forbidden energy gaps of 0.72 electron volts examples and 1.1 electron volts. So energy gap is very less. Energy gap is very less. And it is defined as one in which the number of conduction electrons is equal to the number of volts. Now let us see the extrinsic semiconductors. The intrinsic semiconductors to which some suitable impurity or doping agent or a doping has been added in small amounts, extremely small amounts, 1 in 108. The part is 1 in 108. Imagine how less it is. They are called as the extrinsic or impurity semiconductors. The conduction is due to addition of some impurity. By doping, you get it. So the intrinsic semiconductors generally it is due to the impurity or the doping agent or the doping has been added extremely small quantities is the extrinsic or the impurity semiconductors. Here the large quantities. So semiconductors here impurities are of large quantities are also present. Usually you do the third group elements or the fifth group elements. Based on the impurity present in the extrinsic semiconductor, there are two types. N-type semiconductors and p-type semiconductors. N-type due to the negative charge, p-type due to positive. So what is an N-type? The impurities are told you two types. Donor impurities. The elements which donate excess electrons for conduction. Example, pentavalent elements like antimony, phosphorus, arsenic. The elements which donate excess of electrons for conduction. Example, pentavalent elements like antimony, phosphorus, arsenic. Now coming to the impurities, acceptor impurities. Here are elements which create positive carriers or holes that can accept electrons. Example, trivalent elements like boron, gallium, or indium. Third group elements. Here it is fifth group elements. So how we are getting due to the impurities are of two types. Donor impurities, pentavalent as well as the trivalent. So the donor impurities, those elements which donate excess of electrons for conduction is pentavalent. More number, 5 electrons will be given here. Antimony or phosphorus if you take, they're having 5 valence electrons and if you need the 5 valence electrons, that will acceptor elements here. Get the positive charges carriers or the holes. Accept the electrons here, the less number of elements like boron, gallium, rhodium. These have 3 valence electrons. These are having 3 valence electrons. They create the positive charges or holes that can accept electrons. Now we'll see, depending on the impurities, what are the types of the intrinsic negligible impurity. This is silicon, fourth group element. In this crystal structure, if you see 14, 4 is the valence electron. And in this crystal, there is no extra element. This is a pure form of semiconductor. So it is called as the intrinsic semiconductor. It's called as a intrinsic semiconductor. Here, completely. This is the conduction band. Here. In this silicon, what you do is now you replace this intrinsic with negligible impurities. Now, how do you get from the silicon crystal? How do you get a N type and how do you get a P type? N type, once if you see, this silicon it is having 4 valence electrons. It is having 4 valence electrons. Now, that silicon is replaced from its crystal. You add a phosphorus, yeah, pentavalent element, phosphorus. The donor impurity is phosphorus. Due to the addition of this phosphorus, excess electrons come for the conduction. Actually, the valence electrons are 4, but in place of 4, you're getting the phosphorus 15 and the valence electrons are 5. So in place of 4, you're getting 5. So 1 electron is left extra, and that 1 electron keeps on moving. It comes out of the crystal. Yeah, it's moving around in this crystal. This is entire with donor phosphorus. Now, coming to the P type. P type. In this P type with the acceptor, you see here P type. In this P type, the silicon element, the in place of silicon, it is having 14 electron, 4 valence electrons. The silicon crystal, one of the unit cell, it is replaced by boron. Here, the acceptor impurities, these elements, they create the positive carriers or holes that can accept electrons. So trivalent elements like the boron, gallium, or indium. The trivalent element is being doped. Once if you dope a trivalent element, what is happening in place of 4? You are having only 3 electrons. So 1 electron is deficient. Silicon crystal is deficient of 1 electron. It is deficient of 1 electron. And therefore a hole is created there. In place of 1 minus is less, so we'll be having 1 plus. 1 hole is created, positive charge. So here, due to 1 plus is there, 1 more electron jumps into this hole. Again, a hole is created. Add to this hole another, here, another electron jumps into this hole, and hole is created in another place. So as and when the holes are formed, electrons keep on shifting. So holes are formed in one direction and the electrons are moving in opposite direction. So it is in a hole in one direction and electrons movement is in other direction. So once the electrons are moving, what you call it is the conduction. It is conduction. Similarly, in fifth group elements also, here, when a pentavalent, here, the donor impurities. To donate excess pentavalent electron is excess. So this electron it keeps on moving around the crystal. So this movement of the electron due to extra electron is conduction of electrons. It is due to a negative charged electron. It is due to addition of pentavalent. So it is due to electron minus charged one. So it is an n-type conductor. And here you can see it is the p-type. It is the p-type conductor. Because due to the positive charge, a hole is a positive charge. So hole is formed in one direction and in the hole the electron keeps on moving to the holes. So electrons will be moving to the holes. So hole is in one direction and electrons is in opposite direction. So thereby the movement of the electrons is conduction. N-type is formed due to the negatively charged electron. It is arised when a fourth group element of the semiconductor it is replaced by a pentavalent element. And the p-type it is due to plus charge. It is due to the acceptor. P-type it is due to the acceptor. That is the due to the proton plus charge. Due to positive charge, if you get the type of semiconductor is p-type. If it is due to n-type, you get that is n-type of semiconductor. Due to negative charge, it is n-type. Due to positive charge, it is p-type. If fourth group element is replaced by fifth group, then electron excess minus charge excess due to and that is n-type. And the fourth group is replaced by third group. Hole is created and the moment of the hole creates the moment of the electron. That is due to the positive charge, so we call it as a p-type semiconductors. Now, when a pentavalent here it's getting involved, the covalent bonding. What is happening here? N-type comes from negative charge of the electron. In this semiconductor, electrons are majority carriers. Holes are the minority carriers in the N-type. And type semiconductors are created by doping intrinsic semiconductor with donor impurities. When a pentavalent element such as phosphorus, arsenic, antimony added to intrinsic semiconductor, 4 electrons are involved in the covalent bonding with 4 neighboring pure semiconductor atoms. And the fifth electron is weakly bound to the parent atom, and even for the lesser thermal energy, it is released, leaving the parent atom positively ionized. Yeah, in place of the silicon, the phosphorus, a free electron will be generated, which keeps on moving. So the impure atom, that's phosphorus, induces the free electron. So because it is negatively charged, if the conduction is due to negatively charged species electron, it is called N type of semiconductor. Yeah, I told you N type comes from negative charge of the electron. In semiconductor, electrons are majority carriers and holes are the minor carriers. In intrinsic semiconductors that are with pentavalent N-type semiconductor, energy level of the fifth layer is called donor level. That is the donor. N-type come from the negative charge and the semiconductor electrons, majority carriers, hole are the minority carriers. N-type semiconductors created by doping the intrinsic semiconductor with doping impurity. That's it. electrons from conduction band, and a new band is formed with electrons. So the donor level is close to bottom of the donor level is important. The energy level of the fifth electron is called donor. The donor level it is close to the bottom of the conduction band. It is close to the bottom of the conduction band. Most of the donor level electrons are excited in the conduction band at room temperature and they become majority charged ions. Hence, the n-type semiconductor electrons are majority carriers and hole are minority. The carry part is less. So the donor level is close to the bottom of the conduction band. Most of the donor level electrons are excited in the conduction band at room temperature. They become majority charge carriers. Hence, the n-type semiconductors electrons are majority carriers and the holes minority carriers in the n-type semiconductors. Now coming to the p-type semiconductors. In the n-type, Nd is the donor concentration, that is number of donor atoms per unit volume of the material. Ed is the donor energy. So you will see the carrier concentration of n-type. Consider Nd is the donor concentration. That is number of donor atoms per unit volume of the material. Ed is the donor energy level. At very low temperatures, all donor levels are filled with electrons. At low temperatures, all donor levels get filled up with electrons. And with increase of temperature, more and more donor atoms get ionized, and the density of the electrons in the conduction band increases. So with the increase of temperature, more and more Nd atoms will increase. They get ionized. Density of the electrons in the conduction band will increase. Therefore, you can see N type of conduction. So with the increase of temperature, energy of the Fermi level increases. As the temperature increases, more donor atoms get ionized. Increases the temperature in generation of the electron hole pair due to braiding of the covalent bonds and the materials tends to behave in the intrinsic manner. So the Fermi level moves towards the intrinsic Fermi level E2. Now we'll see what is a p-type. Already explained, but once again in detail. P refers to the positive charge of the hole. In p-type semiconductor, holes are the majority carriers and electrons are the minority carriers. P-type semiconductors created by doping intrinsic semiconductors with acceptor impurities. So p-type refers to the positive charge of the hole. In p-type semiconductors, holes majority carriers, electrons are the minority carriers. P-type semiconductors are created by doping intrinsic semiconductors with acceptor impurities. When a trivalent such as aluminum, gallium, indium have 3 electrons in their outermost orbits, added to the intrinsic semiconductors, 3 electrons of the indium are engaged in covalent bonding with 3 neighboring silicon. So indium needs one more electron to complete its bond. In this electron, it may be supplied by silicon, thereby creating a vacant electron site and hole or on the semiconductor atom. So indium accepts one extra electron. So the energy level of this impurity of the atom is called acceptor level. So indium accepts one extra electron. The energy level of this impurity atom is called acceptor level. And the acceptor level lies just above the valence. So the type of the trivalent impurities are called acceptors. Type of trivalent impurities are called acceptors. Acceptor impurities. And the semiconductors are doped with the acceptor impurities are called p-type semiconductors. So even at relatively low temperatures, these acceptor atoms get ionized, taking electrons from valence bond. and they give rise to holes in valence bond for conduction. So even at relatively low temperatures, acceptor atoms get ionized, taking the electrons from valence bond, and they give rise to the holes in the valence bond for conduction. Due to ionization of acceptor atoms, only holes and no electrons are created. Thus, holes are more in number than electrons. Hence, the holes are majority carriers and the electrons are minority carriers for the P type of semiconductors. The holes are more here. Minority electron, majority of the holes. Here for the P type, as I've told you, holes are, yeah, due to ionization, acceptor electrons, only holes and no electrons are created. No electrons are there, only holes are created. So holes are more in number than electrons. Holes are majority carriers and electrons are minority carriers. So therefore it is called as p-type semiconductors. And whereas in n-type, holes are minor, electrons are major in p-type. Their majority are the electrons and minority are the holes. So this is majority is electrons, negative charge. So you call it as n-type. And this is p-type. So this is the about the semiconductors. So different types of materials were explained by band theory. In that band theory, metals, non-metals, that is insulators, and semiconductors, and the types of semiconductors is explained clearly in this class. Applications you can see organo, nano, radio frequency indication devices, solar cells, organic liquid emitting diodes, organic nano radio frequency indication devices, solar cells, display, transistors you can see, brighter display, thinner display, flexible. So shop wizards. So passive RF devices take outside world, so there will be no need for the scanners. So RFD, RFID, solar cells you can see, light falls on the polymer, electron hole is generated, electron is captured. Okay, electricity is passed through the nanotube. Yeah. Future organic semiconductors can also be seen. Semi, textiles, lab on the chips, and screens, skin cancer treatment also we can observe in future applications for the semiconductors. Organic semiconductors you can see. Polymers, monomers, yes. Field effect transistors you can see. Electron driven organic lasers, organic semiconductors, microwave diodes, all these come under semiconductors. I hope you have understood the class clearly. Semiconductors, types, and how the current is carried, why it is called n-type and p-type. Okay. So, and what are the applications website? Thank you everybody for listening my class so patiently.